Yes. Yeah, so I think on Tuesday I introduced the linear transformations. So let me just remind you very quickly the definition. I think we had probably a couple of examples, but I will first remind you the definition and then I will come back to my examples, right? Yeah, so what I call a linear transformation is, it's a map. So let T from R2 to R2. So again, R2 means the plane. Okay, R2, it's 2 bits because we have two coordinates, obviously, X and Y, or U and V or whatever. We have two coordinates, right? T be a map. Okay. So suppose T of UV is equal to A times U plus B times V, and then C times U plus D times V, right? Where A, B, C, D are constant. So the U and V, they're supposed to be my variables, right? My coordinates. And A, B, C, D are just a constant, right? U and V are are the coordinates or the variables. Okay, so such map T is called linear transformation. So such T is called a linear transformation. Okay, and the thing is, why it's called linear transformation, actually, because you can write T as like a matrix times the coordinates U and V. So we can write, so remark, so why it's called the linear transformation, it's because we can write T as so T of T of UV can be written as matrix. In the first row you have AB, in the second row we have CD times the column with the coordinates UV. So this point here, this is a matrix, matrices multiplication, right? So this is matrices multiplication. Okay. I don't know. I'm not sure if you guys took a linear algebra before, but multiplication between matrices, it's not. There's a very special formula for multiplication between matrices. Like here in this case, you would take the first row here times the first column here, and then you multiply like the A by U plus the B by V. Okay, and then that will be your first the first component. That will be the AU plus BV. Okay, and then you take the second row, which is CD, and you multiply the C by U plus the D by V. Okay, so that's how multiplication between matrices work, right? You have to take like rows in your first matrix and you have to multiply them by the columns in the second matrix. All right. Anyway, it's just for your information, guys. We are not doing linear algebra here, right? I'm just saying why this is called linear transformation. It's because you can write it like some matrix times your variables. Anyway, yeah, so that's why I call it linear transformation. I think we had an example. So I think we discussed this example last time. So T of UV is equal to U plus V, U minus V, right? So in this case, A would be 1, right? AU plus BV, so B would be, the B here would be 1, B. And then the C would be 1 again. So C is equal to 1. All right, and then D, of course, though it would be a negative 1, right? So the D here would be negative 1, right? You need the minus, right? So D is negative 1. It's not 1, it's negative 1, right? Because of the minus. Anyway, so I mean, so it's just you have to multiply your U and V by a constant, right? Yeah. So I actually I think I discussed this theorem on Tuesday. So we said, what's so special about the linear transformations? So this is a theorem. So if you have a linear transformation T, so so let's say you have matrix A. So capital A is the matrix A, B, C, D. Okay, such that we need actually the determinant of A to be non-zero. So determinant A, what's the determinant of A? It's just you cross multiply, like it's like A times D minus B times C. You need the determinant to be non-zero. Okay, and so we have this matrix with a non-zero determinant, and then define, let's say, T of UV as, you know, as a linear transformation given by this matrix A. So T of UV is equal to A times UV. Okay, be linear transformation. Okay. So what's so special about linear transformations? Or how do the linear transformations change, you know, change the regions in the plane? Well, actually, then the T actually takes parallelograms to parallelograms. Okay, remember, like in this example, if we come back to this example with U plus V, U minus V, I think we tried to find the image of the square. Remember, we had this square 0, 1, 0, 1. This is 0, 1 here, 0, 1. Okay, and then the image by the transformation T was also a square, right? So the image was like, this is 1 here, this is 2, and we said this is probably negative 1 here, it's positive 1. So we said the image of this square would be also a square, right, by the transformation T. So it would be this, I think, would be this square here. Okay, so that's what I mean by T takes parallelograms to parallelograms. So it would take, so if you have a parallelogram, then the image would be a parallelogram, right? Here, like in this example here, we have a square, so the image would be a square, etc. Right? And of course, and it takes the vertices of parallelograms to vertices of parallelograms, right? Now, what's really interesting for us is that, well, what's the relation between the areas of the two regions? Like, what would be the relation between, you know, like here, the area of this square it's just 1 times 1, right? It's 1. Now, the area of this one here, the image, the area of the image, we said, I think we conclude this on Tuesday, and we said it's just a square root of 2 times square root of 2. So the area is 2, right? Now, the question is, how can we deduce the relation between the two areas if you know your matrix A, or you know your transformation T? Well, the thing is, so the relation is, so the area of, so if you have so let's say you have a D or R be a parallelogram. Okay. Let me just remind you, the area of a parallelogram is just area of R is just the base times the height, right? That's the area of a parallelogram, right? It's base times the height. Anyway, so if you have this parallelogram R, then the area of the area of R, the area of the image of R by T, of the image of R is equal to actually the absolute value of the determinant of A times the area of R. Okay. So, for example, well, here's a good example. So we have this linear transformation T, right? U plus V. Let me write it down here again. Just enter the theorem so you can see how can we apply such a formula. So, example. Come back to the same example. So it's again, it's T of U V. We said it's U plus V, U minus V, and we said the matrix R would be just 1, 1, 1, negative 1, right? A, B, C, D, right? Anyway, now we have R. So R is the square here, 0, 1, right? So the area of R is 1. Okay. Now, if you want to apply the formula here, this formula here, the area of the image, right? The area of the image of R would be equal to the absolute value of the determinant of A times the area of R, right? The image of R, we said, would be this square here, this one here, the green one, right? This is the image of. This is the image of R, right? Now, let's apply the formula. So what would be the area of the image of R? Well, first, we have to compute the absolute value of the determinant of A, right? So what's the determinant of A? So here's my matrix A. So it's supposed to be AB, first row, second row, supposed to be CD, right? So anyway, determinant of A, by definition, it's just AD minus BC. So in our case, A is 1 times D, which is negative 1, minus B, which is, so you see what I'm talking here, what I'm talking about, guys, here? This is A, this is B, here's C, and here's D, right? So minus, we said minus B, which is 1, times the C, which is again a positive 1. Anyway, so the determinant of A is actually negative 2. Okay, and then absolute value of A, absolute value of the determinant of A is just absolute value of negative 2, which is of course positive 2, right? So if we apply our formula, again, I'm talking about this here, this formula here, right? The area of the image is equal to I should probably zoom out here. Okay, so I'm talking about this formula. Area of the image of R is equal to the absolute value of the determinant of A times the area of R, right? So then, so the area of the image so if you apply the formula, so area of the image is equal to the absolute value of the determinant of A times area of R, and well, the absolute value determinant of A is +2, right? This +2 here, and area of R is our square with side equals to length of the side is equal to 1. So the area for R is 1. So it's 2 times 1. So it's equal to 2, right? And that's exactly what I got here. You know, we said the area of the image is 2, right? So of course the formula works, right? First, any question about this, guys? So you see, so this is nice formula because it relates the area of the image with the area of the original area, right? So why we are interested in the relation between the two areas? Well, it's because, you know, integrals, the first definition of integral is like the area of, you know, of the region bounded by the x-axis and some function f, right? So the integrals are about areas, volumes, etc. So when we're going to make a change of variables, we need this, you know, in some sense, we need to relate the area of the two regions, right? And the area of the two regions is, in this case, when we have a linear transformation, is related by the absolute value of this determinant of A, right? In some sense. So does this make sense to you guys? Anyway, so what's another important thing, actually, another nice property of linear transformations is that they are actually one-to-one. So what do I mean by one-to-one? So let me just remind you. Oops. Okay, so just remind you here, what do I mean by one-to-one maps? So a map T, so this is like a very general definition. So a map T, let's say from R2 to R2 is one-to-one. Okay, if 2 points have the same image, if T of UV is equal to T of U prime V prime, right? Then the UV is equal to U prime V prime. Okay, so what I'm saying here, guys, is that if 2 points, they have the same image, it means that the 2 points are the same. Okay, they must be equal. Okay. So the idea here is that if so one-to-one means that, so if 2 points have the same image, okay, then the 2 points are the same. Then the 2 points are the same. Okay, or in other words, 2 different points, they have two different, two different points, they have two different images, okay? Two different points, then two different images, all right? So two different points, they cannot have the same image in some sense, right? So that's what I mean by one-to-one. And actually, linear transformation with determinant, well, because you may ask why we have this condition that, you know, in this theorem, we have this condition that the determinant of A is non-zero, right? Well, determinant of A is non-zero. It means that actually the transformation T is one-to-one. Okay, so and this is actually, it's not really hard to prove. So we claim, so if T of UV is equal to A times matrix A times UV, so T is linear transformation with determinant of A is non-zero, okay, then T is one-to-one. Okay, so having determinant non-zero means that actually you have a one-to-one map. Is there any question, guys, about these linear transformations? But of course, not all transformations are linear. Okay, so okay, so this is my next remark, and I will do an example. So not of course, so not all transformations are linear ones. Okay, so for example, let me give you an example here, and this is actually would be the definition of polar coordinates, but I will define later polar coordinates anyway. So let's say you have T of r theta. Okay, so here T is a map from, let's say, R2. Okay, so let's say my variables here, instead of UV, I'm gonna call my variables R and theta, right? Let's say T of r theta is equal to R cosine of theta, R sine of theta. Okay, so this is, I mean, this is a map, this is a function, you know, from the plane to the plane, right? I mean, you have two variables, you start with two variables, right? And then you end up with two variables. So it's a map of the plane, right? Now, if you take, for example, I'm gonna take a rectangle and see what happens to the rectangle under this transformation T, okay? So I'm gonna take the rectangle, let's say R, I'm gonna take R to be equal to 1/2 1 cross, let's say 0 pi. Okay, so R here, this is a rectangle. Okay, so when you have an interval across another interval, that's a rectangle, okay, or a square. Or, well, if it's the same interval, of course, that will be the same length, then that will be a square. But anyway, in general, so we have, when you have an interval across another interval, that will be a rectangle. So like here, you can, of course, you can draw this, sketch this rectangle R in the R theta coordinates. So here we have the R, this is R coordinate, and this is the theta coordinate, right? We have two variables, two coordinates, R and theta. So we need R. So my rectangle R is half, the interval half 1. So it means that my variable R belongs to the interval half 1, and my variable theta belongs to the interval 0 pi. All right, so I'm gonna need here, and on the R axis, I'm gonna need half and 1. Okay, because my R belongs to the interval half one, and theta is from 0 to pi. So my theta is, here's 0, and let's say here's pi. You know, pi is 3.14 something, 15, I think 3.14, 15. It's some, you know, it's some decimal. So let's say that's my pi. Anyway, so when you say half times 1/2 times 1/2 1 times the 0 pi, then you get this this rectangle here. So it's this rectangle. So this is here, this is my R, right? That's the half one cross 0 pi. Now my question for you guys, what will be the image of this rectangle R under the transformation T? So now the question is, what's the image of R under the transformation T, right? Remember, like for linear transformations, they take parallelograms to parallelograms. So if you have a rectangle, you're gonna get a rectangle, let's say, okay? But here, in this case, you have this rectangle. Now, if you, so let's say this is your X, R cosine of theta is your X, and R sine of theta is Y. Okay, so here I'm gonna draw two axes. The x-axis here, X is supposed to be equal to R cosine of theta, right? And the Y, it's equal to R sine of theta. Okay. Of course, if X is R cosine of theta, right? And Y is R sine of theta. So if you do, of course, if you do X squared plus Y squared, that will be R squared, right? So in some sense, this R is like the radius of your, so R here, so R, it would be like the radius of your circle, right? Of your radius R, right? That's the radius. So when you say R is between half and 1, it means that the radius R is between half and 1, right? So imagine here's your radius R, this is R here, this is your radius, and we are saying the radius is between half and 1. So you're gonna have like, this is the radius half, and then you have the radius 1. Okay, so when you say radius is between half and 1, it means that you have this whole region here, right? So because if you take any point inside this region, this blue region, then the radius R is between half and 1, right? Next, what about the angle theta, right? So the angle theta is between 0 and pi. Okay, so you're gonna go from the angle 0 to the angle pi, right? So you're gonna go, so theta goes from 0 to pi, right? From 0 to pi. So then the image would be this yellow region here, the half of the annulus, right? So that's so this is going from 0 to pi, right? The angle. So theta here is 0, and here theta is, of course, it's pi, right? Pi is 180 degrees. So so what we are saying here, guys, is that the image of a rectangle, of my rectangle R, it's not a rectangle or a parallelogram. It's actually the half of annulus, right? So it's not, so you see here in this case, you know, the image of a rectangle, so it's not necessarily a rectangle here. It's the image of this rectangle is a half of annulus. So so yeah, so this transformation T is not a linear one, because, you know, for linear transformations, you expect linear transformations, they take parallelograms to parallelograms. But here you are taking this rectangle, the image of this rectangle is not a parallelogram, is actually the half of annulus, right? So obviously this T is not, it's not a linear transformation, right? So the image of the parallelogram R or rectangle R, parallelogram or rectangle R is not, it's not a parallelogram. Okay, actually, so the image is, it's the half or the top of the annulus. So of course, so T is not a linear transformation. Anyway, so does this make sense to you guys? Is there any question about this linear transformation? So again, what I'm saying here is that not all transformations are linear ones, right? Now, yeah, next remark is that you can, I mean, we can extend all these remarks to the dimension theta, right, to the space. We can have the same theorem, same claims in dimension theta, right? So next remark. So we just said not all transformations are linear. Now next remark number 2. Okay, so so here these claims can be extended to dimension 3, to the space. Dimension 3. Okay, the space. Okay, so for example, what would be a linear transformation in dimension 3 in the space? So for example, and I'm going to give you an explicit example. So so of course in dimension 2 here in the plane, you know, we have linear transformation. So we have like a matrix 2 by 2, right? We have a matrix A 2 by 2. In the space or dimension 3, we're going to have a matrix 3 by 3, right? So a linear, for example, a linear transformation T in the space is of the form you know, let's say T of U V W is equal to matrix capital A times U V W. Again, this dot here, it's a multiplication between matrices, right? Multiplication between matrices. Right? So we're gonna have A capital A, where A is, you know, 3 by 3 matrix. So it's like, well, 3 by 3, that would be like nine entries. You know, A, B, C, D, E, F, you know, G, H, I, for example, times, yeah, no times. So that's your 3 by 3 matrix, right? So like, your T of UVW would be like well, it's going to be a long expression here. I mean, so it's like AU plus BV plus CW. That's first component. Second component, you're going to take the second row, like DU, plus EV plus FW. And then third component would be like GU plus HV plus I times W, right? Anyway, so for example, let's just take a numerical example. A numerical example would be example. So then TUVW is equal to 2 times U plus, let's say, 3V plus W, 3W. Okay, so A is actually, you need to find A, B, C, right, etc. Right? You need to find A, B, C. That will be your first row. Like here in this case, that's 2. There's no V, there's no W in the first component, so that will be just 2, 0, 0, right? Second row, that will be D, E, F. This D here, E and F, so there'll be 2, 3, 1. So 2, 3, 1, and finally, last row, G, H, and I. G, H, and I. G and H both are 0, but I is actually 3, so that will be 0, 0, 3. Okay, so that will be your matrix A. And of course, we can talk about determinant of the matrix. Actually, whenever you have like a square matrix, you can always define the determinant of the matrix. But in this case, the determinant of A, determinant of A is like, all right, so let me just probably write down the formula for you. But it's like, so the determinant of A, so the formula is the following. So it should be A times EI minus HF. So you see this, here's your A. So then you have A, and then you take the this matrix here 2 by 2, and you cross multiply, right? So A times the determinant of this matrix 2 by 2, okay? And then you move to the B. Let's say here's B. So if you take B, then you have to take you take the matrix with 2 by 2 matrix, which is like a D, G, F, and I, right? So you're gonna need, and there's a minus here, or a plus, depends on how you write the formula. But let's say I'm gonna go with the plus. So if you go with the plus, then you should have like F, G minus DI, all right? And finally, now if you take the last number here in the first row, C, then you're gonna take this matrix DGEH, all right? And you cross multiply. So that would be like plus C, DH minus EG. Anyway, so all I'm saying, guys, is that you can also compute the determinant of a 3 by 3 matrix. Like here, if you can try to apply this formula for this matrix A. So in this case, if you compute the determinant, then that will be equal to, so like in this case, determinant of A, capital A. So lowercase a is 2. So it's 2 times, 3 E and I. Oops. E and I both are equal to 3. So it's like, so here it's like 3 times 3 minus 1 times 0, and then plus B. B anyway is 0, right? B is 0. So wherever B times wherever, so 0 times wherever is going to be just 0. plus, and again, you're going to have C, and C is also 0. So 0 times wherever is going to be 0. So like in this case, in this numerical example, determinant of A is actually equal to 18. Right? And it's non-zero. So you can say, like in this case, your transformation actually, your transformation T is 1-to-1 because the determinant is not 0, right? So T is actually 1-to-1 because the determinant is non-zero. Right? Determinant of A is not 0. It's actually positive 18. Right, and of course, instead of parallelograms, like in the plane, we talk about parallelograms. In the space, if you want to extend parallelograms to the space, that will be parallelepipeds, right? So T would takes parallelepipeds to parallelepipeds. E here, I, oops, pipets, all right. So what do I mean by parallelepipeds? Well, it's just sort of box, right, in the space. So you're gonna have like something like this here. Okay, so that's what I call it, parallelepipeds, right? So it's just like sort of boxes, right, in the space. And anyway, is there any question, guys, about these linear transformations? I mean, I can, of course, I can prove, we didn't prove the theorem here, which says that, if you have a linear transformation, then it's a 1-to-1. If you have a linear transformation with the determinant of matrix is non-zero, then it's 1-to-1. That's actually not really hard to prove. And you can also prove that, it takes parallelograms to parallelograms, et cetera, et cetera. And what's really interesting for us is this relation between the two areas, right? We said the area of the image would be equal to the area of the image would be equal to the absolute value of the determinant of the matrix times the area of the initial region, right? And it's also not really hard to prove, but it's kind of a long proof. All right. So now the big question is, what happens to the integrals when we transform the coordinates, when we apply these transformations? Okay, so now the question. So the big question we're going to try to answer, the question is, what happens to the integrals when we apply, or when we transform, the coordinates, or when we change the coordinates, when we transform the coordinates. Okay, so what do I mean here by transforming the coordinates? Like in this case, for example, like in this example with r theta, and then this example, t of r theta equals to r cosine of theta, r sine of theta, right? So we started with two coordinates or two variables, r and theta, okay? And then we do some, we transform these two coordinates into like two new coordinates. Like here you have this is first component is this your new coordinate, r cosine of theta, and we call it x. And the second component, or the second new coordinate, which is equal to r sine of theta, that's like your new coordinate y, right? So we are transforming the coordinates here, okay? We are going from r theta to x, which is r cosine of theta, and y, which is r sine of theta, right? So we are transforming coordinates here. Anyway, so the big question, of course, now is what happens to the integrals when we transform the coordinates? So that's actually the section 6.2, 6.3. So we're gonna see what happens to the double and triple integrals when we apply a change of variables, okay? Or when we transform the coordinates. Right? Is there any question, guys, about these linear transformations?
No.
All right, so then let's move to the next section. So here in this section, we're going to try to answer this big question about the double, triple integrals. But I'm going to start with the single variable. I mean, the single variable, like integral of functions with a single variable. And you'll see how we extend what happens in the case of single variable to the double and the triple integrals. So this is kind of like 6.2 and 6.3 combined there, because they are kind of related. So yeah, this is change of variables. So let me start with the single variable. Okay, that's something that you really know by heart, I guess. Single variable. So change of variable would be just a substitution. Okay, so for example, let's say you have this integral from 0 to 2, 2x, and then cosine of x squared dx. Right, so this is a function of single variable. We have only one variable, x. All right, so the variable here is x. Okay, so we have just one variable. Anyway, of course, dx, this is important actually. So this dx, this is supposed to represent the length element, right? So dx is the length element. Remember, guys, I mean, I think like probably the first week of this semester, we discussed a little bit the case of I actually recall the integral of single variable, right? And in the definition of the integral of single variable, we said that this dx represent the length element, because of course it allows you to compute the length of your interval, right? It's so when you do the integral from 0 to 2 of dx, just dx, right? The answer would be equal to 2. Okay, the 2, that's the length of your interval. Okay, so this dx is supposed to have, I mean, geometrically, so we have this interval 0, 2. This is 0, 2. All right, and dx, when you say dx is supposed to represent like a variation in the length of your subintervals, right? This is supposed to be like dx. Of course, the length must go to actually to 0, but that's actually what dx represent, right? And when you integrate dx, so you have to think of the integral as, as this Riemann sum, right? It's like saying Riemann sum. It's like saying this dx plus this dx plus another dx, plus another dx plus dx, etc., etc. So we have this Riemann sum Okay, and then so the total would be equal to 2, right? Makes sense, right? So, the Riemann sum, of course, you need the limit of the length of this subinterval of this dx to go to 0. So you need this dx to go to 0. So this equal to 2. All right. Anyway, now, of course, now how do we compute this integral? This 2x. So let me come back to this, my initial integral here. 2x cosine of x squared. Of course, you can think of a substitution here, right? You can just, so we can do the substitution like u equals to x squared. Okay. So when you do actually this substitution, u equals to x squared, you are actually doing a change of variables, right? You go from this variable x to this variable u, right? This is a change of variables. This is a change of variables, right? You are changing x to u, right? Now, that's a change of variable. And you can even say that this is actually like the transformation. So we are saying like t of x is equal to x squared. So this x squared is your new variable, which is u. Okay. So we have a transformation here. We are transforming this x into u, right, which is x squared. Anyway, so now when you compute the derivative, right, we have to you want to do this substitution, use x squared. That's excellent. But then if you do du, so derivative of u, so then du, derivative of u, I mean u is equal to x squared, right? So then if you do du dx, derivative, this is u prime of x, right? This is derivative of u with respect to x, u prime of x. Du over dx is equal to 2x, okay? Or if you prefer, du is equal to, sorry, 2x here, is equal to 2x dx. Okay. So now, guys, so you must understand that in x coordinate, the dx, that's the length element, right? In x coordinate, this is my length element, right? This is the length element in the x coordinate, right? Now the length element in the u coordinate, right? You have this new variable u is the du. So this du is the length element in u coordinate, right? And again, guys, you have to keep in mind, what do I mean by length element? Length element like dx would represent just this small, this small variation in the length of your subintervals, right? That's your length element dx. Now I'm going to change that to a new variable, u. Now, so we have this relation between the length element in x coordinate and the length element in u coordinate, and the relation is given by this 2x. So this 2x, so this 2x measure actually how length. So this 2x, it measures how the length in the, let's say, in the u direction, or in the u coordinate. The u direction relates to the length or length element in the x direction, right? So what we are saying, guys, is that the relation between the two length elements is given by this 2x. That's exactly the relation, right? Or the ratio, right? So this 2x actually represent like the infinitesimal, let's say, length distortion factor, or in other words, just the the relation between your length elements, right, in the x and the y coordinate. Anyway, I'm not well, this is supposed to be my substitution, and of course once you make the substitution, then the integral is very easy to compute, right? Though then the integral will be just then this this 2x squared cosine x squared dx. Once you do the change of the variable or the substitution, then that will be just cosine of u, du, and that's just a sine of u plus constant. Anyway, so all we are saying, guys, here is that this is an important thing here is that using this substitution, then the integral is now kind of easy to evaluate, right? So now the question is, how does this work in double and triple integrals, right? So the question now is, so how does this work in double and triple integrals? Okay. So we're going to suppose that we have sort of substitution in dimension 2. So we suppose we have like a change of variables. So the answer. So suppose we have a change of variables given. So we're going to start first with the double integrals, right? First, so this is, so I'm going to start first with the double integrals. So this is the answer. So first, this is the double. Okay, double integrals. So suppose we have a change of variables given by the transformation. Let's say t of uv, right? We are in the dimension 2. We have two variables, is equal to, so here the first component is going to be some function of u and v, right? So let's call this function x of u and v. So x of u and v, this is my first function. And then the second function or the second component is some function of u and v. And we're going to call this second function y of u and v. All right, we have these two functions. First component, that's my function x, function x function of u and v, and second component is my function y, and it's a function of u and v, right? Now, so to do this change of variables in the double integrals, so we're going to need the Jacobian. So definition. And we're going to have a couple of examples, of course. But first, let me write down the definition of the Jacobian. So the Jacobian of t. So actually, the word Jacobian comes from Jacobi, who's a German mathematician, right? This Jacobian, actually, this comes from Jacobi, who's a German mathematician of 19th century, actually. Anyway, so the Jacobian of T, of the transformation T, is, well, I'm going to introduce first the notation. So is denoted by, so we're going to have partial, so x and y, and partial u and v. So this is the notation for the Jacobian, of course, in dimension 2. So this is my Jacobian. So this is what I call, this is the notation for Jacobian. And this Jacobian is actually the determinant of, and you can see here somehow there's this relation with the linear transformations, right? I mean, here T, it's not necessarily a linear transformation. But in case of linear transformation, we said the relation between the areas of the two regions, I mean, the initial region and the image, is given by this absolute value of the determinant of their matrix. So here's the same thing. Same thing happens here. So if you have this transformation T, which is not necessarily a linear one, but still, we're gonna need the determinant of. So is the determinant of. So let me just write it down here for you. So this partial x, y, partial u, v. This is the determinant of the derivative matrix. So it's delta x, delta u. So the partial derivative of x with respect to u. Then we have partial derivative of x with respect to v in the first row. And in the second row, we have partial derivative of y with respect to u and partial derivative of y with respect to v. Okay. So determinant of this matrix, which is, in other words, this is partial x, partial u, partial derivative of x with respect to u, times partial derivative of y with respect to v, minus partial x, partial v, partial y, partial u. Okay. And I'll explain in a minute, but this Jacobian, I mean, the geometric interpretation of the Jacobian is that it actually measures how the area in the xy coordinate. So this determinant here, this Jacobian here, this determinant here, it measures how the area in the x, y coordinates relates to the area in the u-v coordinates. Okay. So what I'm saying, guys, is that so the idea is actually the following, right? So so what we are saying is that, so we have first the u and v coordinates, right? And you have some region here. Let's say you have this rectangle or wherever. Okay, I have this region, right? Now, what's the area element in the UV coordinate? So when we have, when we have two coordinates, two variables, what will be the area element here with the U and V? It's just du times dv, all right? So it's du dv, right? That's my area element. When you have two variables, u and v, area element is du dv or dv du, right? Depends. But what does it represent this? What does it represent this du dv? Well, it's just, you know, you have du. This is supposed to be like du, right? And this is supposed to be your dv. So when you do du dv, this is like very small. You have like very small rectangle here, or a square. Okay. So again, this is like, you know, like in a single variable, we have this very, very small subinterval, right? Dx. Now, two variables, we are talking about areas, right? Not length. We have area, and we have this du dv would represent an area element, which is just a very small, you know, very small rectangle or a square in your region, right? And now what we are doing is that we are transforming the coordinates. So now we have like new variables, right? This is my x, this is my y. X and y both are functions of u and v. So this is x, which is function of u and v, and this y is also a function of u and v, right? Now you do some transformation to this rectangle or wherever region you have. You know, you have this transformation t, okay, and then you get some new region. Let's say I don't know, some parallelogram or wherever, right? This is your new region, right? This is the image of your rectangle, right? Now, the area element in the new coordinates, it's, as I said, it's supposed to be dx dy, right? So here's your dx, and here is your dy. Okay, and what I'm saying here, guys, with this Jacobian, so the geometric interpretation of the Jacobian is that it relates the area element in the uv coordinate to the area element in the xy coordinate. So what I'm saying is that the relation between the area, so this small rectangle here in the uv du dv, right? So the area of this small rectangle would be equal to, it's related, or probably here 1 over, but anyway, so this is here, you're going to have your Jacobian. Okay, and then you have the area of your, probably I should change the color here. So this is your Jacobian. You have your Jacobian here. It gives you a relation between the area of du cross dv with the area of dx cross dy. All right. So this Jacobian, we're going to use this Jacobian, you know, to relate the areas, the two areas, right? The areas of this. This is a small, very small rectangle or parallelogram. All right. So this is like saying, like for linear transformation. Remember, in linear transformation, if you have a linear transformation, well, then you know, you have this formula between the areas of the two regions. But here we are talking about a random transformation. So it's not necessarily a linear transformation. This is it's a random transformation, not necessarily linear, right? Now, so the theorem. So if you have a double integral and you do a change of variable, so suppose we have a change of variables. So t of uv is equal to first component x, some function of u and v, second component y, some function of u and v. So we have this transformation T. We need T to be 1-to-1. Okay, we need T to be 1-to-1. This is really important. Okay. And suppose that R is some region in the plane. And D is its image by T. D is the image of R by the transformation T. This is the image of R under T, right? So we have this region R, and the capital D is its image by the transformation T. Now, suppose you have a function of two variables. Suppose f of xy is a continuous function. So here f is a function of x and y, right? Then the integral of f over the region D. So the region D is the image of the region R, right? So but D, so it's in the xy, D is the xy coordinates, right? So the image, so the double integral of the function f dx dy in over the region D is equal to the double integral of the function f of x uv y uv, right? X and y, they're supposed to be both functions of uv, right? So we can substitute x with uv and y with the uv, right? This new function, this function f now expressed in terms of u and v over the region R. And then you have the Jacobian. So the change of variable here, when you do the substitution, you're going to need the Jacobian. So you're going to need actually the absolute value here. You're going to need the absolute value of the Jacobian. So partial xy, partial uv, and then du dv. Du dv. All right. So this is sort of change of variable in dimension 2, right? I'm gonna do some numerical example. I have 4 minutes. I'm probably gonna need more than 4 minutes to do my example. Sorry, to do my example, but let me see. Yeah. Well, let me just say, well, before my example in dimension 2, let me just say that for single variable, right? You have this, we have this integral, 2x cosine of x squared over this interval 0 to dx, right? And then you want to go from, so here you're going to go from x to, let's say, u, right? So in case of single variable, so you can just probably forget about the y here in this dimension 2, right? You can just forget about the y, right? This y here, there's only u. You can forget about the v, right? So you do this transformation, u equals to x squared, all right? or in other words, you can, if you want to, so you can express x in terms of u. So x would be plus or minus square root of u, but x is between 0 and 2. So x is positive, right? So it's plus square root of u. But anyway, so if you do the Jacobian here, in this case, the Jacobian for a single variable, so the Jacobian would be just partial x, partial u, okay? Like, again, here, this is a formula for like when you have two variables, right? So I just forget about the y and v. Suppose you have just one single variable, right? Just x and u. So then the Jacobian is just partial x, partial u. So what would be partial x, partial u? Well, it's just, that would be equal to, well, you need the absolute value, of course. So that's derivative of this square root of u. That's half, half u to the power negative half, right? So now, if you apply this, this formula with the Jacobian for a single variable, you're going to have like, you have this function 2x cosine of x squared, right? Dx, of course. Then suppose now we are supposed to have this. So x is the square root of u, right? So 2x, that would be 2 square root of u cosine of, I'm going to express everything in terms of u, right? Cosine of x squared is equal to u. So here's my u. Now, what's dx? Well, dx, well, not dx, but I'm applying this formula. So here, I'm going to need now, my Jacobian. So my Jacobian would be half. So here we're supposed to have the Jacobian, right? So it's half u to the negative half, and then du, right? This is supposed to be my Jacobian, right? This is Jacobian. Now we can see, this 2 with the half, they cancel out. This square root of u with this u to the negative half, they cancel out. So now it's just cosine of u du. And that's exactly my substitution, right? So you see, my formula in the two variables here, double integral. If you want to apply the same formula in the like for single variable, you can just forget about the u and v, and you get exactly the substitution like for single variables, right? So this is exactly when you do this substitution, u equals to x squared, right? You're gonna get the same. You get the same answer, right? That's exactly my substitution, right? Okay, so so what I'm saying here, guys, remark is that we can apply our formula for function single variable, right? We can apply formula for functions of single variable. So you can just forget about the x. Forget u. The y and the v, right? You only have x and u, right? Anyway, I'm gonna stop here, guys. So next time, we're gonna have numerical examples of this formula for the double integrals. And then we're going to have a similar formula. We're going to extend this formula for 3 variables in case of 3 variables, right? So yeah, so I'm going to stop here. As I expected, I didn't finish this section, this change of variables section today. So I won't assign a new homework actually, because homework number 3 is supposed to be about this change of variables, right? That's and we didn't finish this change of variables. We just started actually. So yeah, so I won't assign new homework this week, but I will, of course, next week. Okay. Thank you, everyone. And I guess I will see you next Tuesday. If you have questions, guys, about, again, you have still questions about the homework, let me know. I mean, you have, the whole day to finish your homework. I mean, no worries. Even if it's after 4 or 6 p.m., it's not a problem. All right.
Thank you, Professor.
Thank you, David. Thank you, everyone. Appreciate it. Take care and stay warm.
Likewise.
Bye, Professor.
Bye. See you next time.